Hey BI 101ers, it's Dr. Duncan here. We're going to start a new class here learning about geology. Now you might be wondering, what the heck does geology have to do with biology? Well, we're going to be intersecting with geology on several levels this course, one of which is to understand evolution, which involves explaining why there's so many species on Earth and why there's so many species in Alabama. And a lot of the answer to that question involves geology, because geology has shaped the landscape that has produced so many species in the state. Furthermore, we're going to be needing some background and understanding of geology to understand climate change and how climate change is affecting the Earth. It's helpful for us to have an understanding of Earth's deep time history. So there are several reasons why we need to understand a bit about geology. So the good news is that I don't have any strong or deep background in geology. I know just enough to get me into trouble, and but also just enough to introduce students to these fundamentals. So let's get started. Okay. So one of the cool things about geology is that, at least I think it's cool, that when I used to think about geology, I thought it was just about rocks and volcanoes and things like that. But as it turns out, life has been shaping the geology of the planet just as much as the planet's geology has been shaping life. We'll see more about that in the subsequent classes, where we go through a tour of Earth's evolutionary history. So we got to cover some of these basics about geology and rocks and things like that in order to appreciate all that. Okay. So the other thing about geology and geologic processes we're going to be learning about is that geology creates the current terrain that we see today. Like this picture you see here from Mount at Cheaha State Park here in Alabama, the highest point in Alabama. Okay. By the end of this and the next unit, you're going to be familiar with the geologic timeline. Think of this as a calendar for Earth's history as depicted by geologists. Now you see two panels here. There's the one on the left that's bordered in blue and the one that's on the right. Okay, those actually connect. They connect at right about here at the bottom. So this, you see it small print at the very bottom, says continued on another side. Well, that's the continuation up here. So you go from the Cambrian right here at 542 million years ago to the end of the Proterozoic eon, which is right up about there. Okay, so it's this long continuous timeline. Now there is a lot of data in this timeline, and I would be even more cruel and unusual than I already am if I were to ask you to memorize everything here. So I've gone through and made a list of exactly what it is I want you to learn about this timeline, okay? I want you to learn the 4 eons that break up our Earth's time and the 3 most recent eras. So that would be the Cenozoic, the Mesozoic, and the Paleozoic. And then I want you to learn the 12 most recent periods, which include the Pennsylvanian and Mississippian subperiods. So this column here shows you the periods, and you'll see, for example, if you go back to the Carboniferous, right here, the Carboniferous period, it's subdivided into Mississippian and Pennsylvanian. The reason the subdivision is that some really cool stuff happens in Alabama in the Mississippian, and then different stuff in the Pennsylvanian. So if we're going to understand things in Alabama, we got to dig in deep there a little bit. Okay. So for each of these time periods, I want you to know the relative sequence. So for example, that the Triassic comes before the Jurassic. That's what I mean by relative sequence. I want you to learn the nested pattern here of the hierarchy. So for example, the Phanerozoic eon has nested within it the Paleozoic era, the Mesozoic era, and the Cenozoic era. And the Cenozoic era is divided into the Tertiary and the Quaternary, and the Quaternary is divided into the Holocene and Pleistocene. We'll be learning a lot more about Holocene and Pleistocene when we get into climate change, okay? Here's what you don't need to know about this. You don't need to know any of these other periods or eras that are earlier than the Cambrian. And so the Cambrian is right down here, starting at 542 million years ago. And you don't need to know the dates of time units, etc., etc. Like you don't need to know the dates unless, and this is a big unless I call them out and I say, hey, this is one that you need to know. And it might be one that I say in the video lecture, or it might be one that's on the slide. Okay, so that's what you're up against here in terms of what I want you to learn. Let's see. I wanted to point out one more thing. Yes, these timeline dates here. Okay, they're measured in. These are millions of years. Okay, so for example, this one right here is 443.7 million years ago. That it marks the beginning of the Silurian period. Okay, so that's what that line represents there, the beginning of the Silurian period. And you should let me also make it clear in case it wasn't obvious. Time is moving from the bottom towards the top on these bars. So right up here at the tip of my pointer, that would represent the current time period. And as I move down this long line here, we're going deep back through time, and then we have to scoot all the way up to here to go to the very beginning of time, which is down here at 4.6 billion years ago, the date that we think that Earth formed. Okay. All right, so here's some overarching concepts that we're going to learn about geology, that there are these things called tectonic plates and that they move around, and that the Earth is dynamic with magma and the plates moving beneath our feet. And there's these processes of weathering, erosion, and deposition, which wind up leading to the formation and then the deterioration of different types of rocks, which we'll also learn about. Okay. Now all this happens because Earth has this crusty, cool outer core. Think about it like the peel of an orange, and then the inside of the orange, the inside of the Earth, is very hot with liquid, a liquid mantle. This is molten rock material that's here, and then at the very inside, you can think of like the seeds that you might find at the center of an orange. That would be like the inner core. It's under such pressure that there's no room for movement. It is solid. So you got the Earth's core that's in the gray zone here. You've got, and the outer part of the core is molten. It's liquid. There's enough. The pressure's still super intense, but it's not as bad. So it winds up allowing that rock to be liquid still. And then you get the mantle, and as you get closer and closer to the surface, the rocks become less liquid-like and more sort of sticky plastic-like. It's still flexible and fluid, but not as much as it is deeper. Okay, so I do want you to learn these different terms for these different layers. Some textbooks and things that you'll see will talk about the lithosphere as opposed to the asthenosphere. The lithosphere being that sort of rigid section of the outer part of the planet that's cooled. The tectonic plates that float around on the Earth's surface are part of the lithosphere. Whereas the asthenosphere is the hot and fluid or semi-fluid portions of the planet between the lithosphere and the core. And what I want you to grasp here is that these continental plates on the surface, these cool rock, this cool material, and by cool I mean temperature-wise, not like cool as in hey man, that's really cool. But this stuff, it basically is floating on liquid rock that's deep below the Earth's surface, and that's what's here in the asthenosphere, which is part of the mantle. Okay, let's move on. Let's see how this all fits together. Hopefully you remember when we studied the Earth's climate that there was these convection zones in the Earth's atmosphere where warm air rises and cool air sinks, and then because the Earth is a big loop in cross section, you wind up having these cells develop. That there's 3 in the northern hemisphere and 3 in the southern hemisphere. Well, as it turns out, there's similar things happening beneath our feet. Hot molten rock rises up and approaches the surface. It dumps some of its heat up at the surface, and then it's cool again and it falls down deeper. And so you wind up having that whole process of heat transfer is called convection in physics, and convection cells are the movements of material, whether it's atmosphere or it's the ocean or it's this rocky material. These are called convection cells. As heated materials rise up, it cools, and then cool materials drop back down. All right. Now, what's cool is, okay, and that meant I meant interesting there. What's interesting here is that you have this going on underneath us all the time, and it creates the landforms that we find on the surface. Here, for example, we see this mid-oceanic ridge like the one we have out in the middle of it, the Atlantic, and the seafloor is spreading to the east and west away from that mid-oceanic ridge. And that ridge is there because of this upwelling of molten material that comes up to the surface, and some of it cools and becomes new rock right about there, and then that rock gets pushed to the left or pushed to the right by new rock that's rising up underneath it. Okay. All right, so that's going on at this very slow, gradual pace on our planet all over. The new term here is tectonic plates. The Earth's lithosphere isn't just one big old slab of cooled rock. It's actually divided into different plates, kind of like if you've ever seen the skull, like a human skull. There's these different plates on it, and they kind of have sutures, like the sort of where they link up together. It's kind of the same sort of thing. So on the outside it's sort of hard and crusty, and it's in these plates, and then on the inside it's kind of soft and squishy. Whether you're thinking about an orange with orange rind or the human skull, soft and squishy on the inside, either way it's the same kind of metaphor there. Okay. Now, different from your skull and mine, hopefully, is that these tectonic plates, as they're called, they float around. They float around because they're basically rafting on all that molten material. I went back a slide here. They're basically rafting on all this molten, basically like a sea of liquid rock underneath the Earth's surface, and they kind of float around, like I said. Okay. The word continent refers to sections of tectonic plates that are really thick with a lot of material on them, so much that they sort of bulge up higher than the surrounding landscape. And that's why we have Asia and Europe and Africa and Antarctica and North America and all that sort of thing. And plates, tectonic plates that have a continent on them, we refer to them as continental plates. I bet you couldn't have guessed that on your own, right? Okay. So there are continental plates, and there are also non-continental plates. I'm sure geologists have a special name for them. I don't know what it is. You don't need to know what it is either. But looking at this map, can you pick one out? There's a few that are on here. All right. And yes, of course, if you're looking at North America, you might be thinking, well, is that a continental plate or not? Because there's so much ocean there. And folks, I can't begin to explain why there's so much ocean on this ginormous continental plate. It is considered a continental plate, and you and I will just have to accept the word of geologists for that. Okay. All right. So you're familiar with these things, volcanoes, right? This is places on the Earth's surface where there's weaknesses in the Earth's crust, and it allows that molten liquid rock to rise up to the surface and spill out. Sometimes it makes it all the way to the surface, like you see here, which is pretty cool to see. Sometimes it rises up and spills out on the seafloor, and so you have underwater volcanoes in some of the oceans of the world. And sometimes it just sort of like pools up underneath the surface on a continental plate and doesn't quite make it all the way up to the surface. That's okay. We still consider those volcanoes, and it still adds to Earth's crust. Okay. Now, these volcanoes, they're particularly common along certain portions of the Earth's surface, especially where those continental plates come together. So check out this map. This is a map showing where all the major volcanoes of the world are. Wouldn't it be cool to have like an endless amount of money and time and get to visit all the volcanoes of the world? Yeah, that's a fantasy life for me. That would be so cool to do. So what you're looking at here is the blue dots are the volcanoes. And another geologic process you're probably familiar with are earthquakes, where the Earth's crust starts rumbling and jolting around and things like that. And where there are major earthquake centers is where you have the red dots. And you'll notice that the earthquakes and the volcanoes are all kind of like, well, not all, but many of them are sort of lined up on the same zone. And that is not a coincidence because those are appearing at the margins of the tectonic plates. So for example, check out here off the coast of South America, you've got all these volcanoes in blue and all these centers of earthquake activity here, and then it juts out here and then up there and then over there. Okay, so you kind of got this sort of rhomboidal shape zone here. Well, let's go back a couple slides and look at that. That's the Nazca plate right there off of South America. Okay. So, in fact, by mapping this stuff out is one of the ways geologists were able to come up with maps like this that show where the edges of the tectonic plates are. We have much more sophisticated methods for doing that now, but this is just mapping this stuff out was one of the early ones. Okay. All right, now the movement of the plates across the Earth's surface help generate some things that are important for shaping the landscape on which we humans dwell. And there's three different types of places where the tectonic plates kind of bump up together. Three different types of collision zones, if you will. We're going to go through each of them. The first you've already seen in a previous slide. It's called a divergent plate boundary. This happens out on the oceans where the Earth's crust is very thin. It's thin because the ocean, the mass of all that water, squishes it flat. Kind of like if you were making dough, you had dough like for bread or for pie crust or something like that, and you like push down on it, it would get really thin, right? Well, if it's really thin, it makes it really easy for that magma to pop up and come to the surface, and that's exactly what happens. So there's a few places on the Earth where that happens. One of those is the Mid-Atlantic Ridge, mentioned already. So on this map to the right, you see Eastern North America. Here is South America here, and then Africa over there, and then a little bit of Europe peeking in on the right. And this map here shows you the mid-oceanic ridge, where what's happening is depicted in this cartoon on the left. Remember, this is a zone of upwelling of materials. Some of it cools and forms new oceanic crust, and then the crust just keeps moving along to the east or the west, depending. Okay, so that's one of the types of boundaries between tectonic plates. This is a spreading boundary, a divergent plate boundary. Another one is where the tectonic plates collide with one another head on. Oftentimes, this is where an oceanic crustal plate rams into a continental plate and a continental tectonic plate. And that's what we see represented in this cartoon. And oceanic crust plates are much thinner than continental plates. I mentioned why earlier. That was my reference to like kneading dough, if you think about it like that. And because they're thinner, they have less mass. And because they have less mass, they get deflected when they run into a continental crust. So they collide, and the smaller, thinner, weaker crust gets shoved underneath the continental crust. And that's what you're seeing here with the lithosphere, that cooled rock that's actually solid rock that's floating above the asthenosphere, that liquid kind of plasticky. I say plasticky, meaning it's just flexible, but it's like it's a molten or semi-molten rock, the asthenosphere here. Okay, and this sort of action creates a lot of the world's major mountain chains, where these continents have collided head-on like this. And one of the things that you see is that offshore you get these deep trenches that suddenly drop off, like a couple miles deep, where even though you're within sight of land and stuff like that, and you get that on places like the California coast, which used to be a subduction zone. It's not anymore, I think. Don't quote me on that, and I won't test you on that, but I think long ago California used to be a subduction zone. It certainly looks like one with regard to this. Let's see, what else do you need to know here? Yeah, okay, so that last point, oceanic crust is then recycled. So this lithosphere, as it gets deflected down, it remelts down here in the asthenosphere and becomes liquid rock, and then starts doing all those things that all the liquid rock does, like moving around and getting caught up in convection cells and things like that. Now, this process is messy and it varies over time and over geography and stuff like that. And as a consequence, you get a lot of debris building up, where I'm kind of showing you with my cursor right now. That debris is what we call mountains. So where you have these subduction zones, you often have a big old tall mountain range along there. And so that's some of the major mountain ranges of the world are as a result of this. Okay, so we've got divergent plate boundaries, we got subduction zones where they're ramming head on. One last one, and it's a transform fault. This is where tectonic plates are sliding past one another. It's not a smooth, gradual process. What happens is that because the edge along here is all rock, it's very resistant to smooth. It's not like it's gliding past, they're gliding, the tectonic plates are gliding past one another. Instead, what will happen is pressure will build up, and then all of a sudden they'll slip, and one jumps ahead in one direction and the other jumps in the other direction. Or maybe one's like solid and doesn't move, and the other one is the one that does all the moving. Either way, what you get with those slippages is an earthquake. So we see a lot of earthquake activity along these transform faults. This is what we have here at in California. You've got a sliding, you have bits of continental plates sliding past one another, and you can see that in the high altitude photograph that you have on the left is a picture of the San Andreas Fault, the big fault that's found out in California, and all that distortion to the Earth's crust that look like hills and mountains and ravines and all that. All of that is the result of this transform fault. And if you look at the map on the right, some satellite imagery that's been colored in and superimposed with arrows and stuff, it shows you the path of that San Andreas Fault. If you ever visit or move to California, be careful where you live and be ready for earthquakes. It's inevitable that there will be earthquakes out there. Just make sure you're ready for it. Okay, make sure you're in a building that's appropriately safe for that. All right, moving on. Earthquakes are not just something for California and faraway places. They actually occur in Birmingham and this other portions of the southeast. This was from February to May in 2012 and 2013, showing you the number of earthquakes that occurred between February 2013 and May 2012. And what you see there is not even over the span of a year. I said May, whatever. I got the dates all mixed up. It doesn't matter. The point is, Birmingham gets earthquakes, and yet this area is considered a relatively stable area on the planet. So if you can imagine this many earthquakes in Birmingham, imagine what it's like living in some of the places of the world where there's a lot more earthquake action. Now you might notice that the magnitude of these earthquakes, which is this column I'm circling here with my cursor, they're all like 4 point something to max like 5 point something. Those are, you can barely feel those at the surface. So these are all like really tiny earthquakes. Okay. All right, so let's talk about the speed of tectonic plate movement. This has a lot to do with what has influenced where life has occurred on the planet and what that life is doing. And we're talking about Earth being about 4.6 billion with a B, billion years old. That is a long time. And small processes that accumulate on a very small scale relative to human time can be magnified over long periods of time. So let me give you, and that's one of the challenges of thinking about geologic time. That video that you're going to watch, that skunk bear video, kind of helps you visualize that. Here's another way to visualize it, okay? Let's imagine that the leading edge of a tectonic plate is moving at 5 millimeters a year. So that's barely, that's not even the width of your tiniest fingernail, okay? 5 millimeters a year. And it does that for 1 million years, which is clearly a long amount of time. But the Earth is 4.6 billion years old. That's 4,600 million years old, to put it in terms of millions of years. So you accumulate 5 millimeters a year over 1 million years, which is just a blip in Earth's time. That plate will have moved a total of 3.1 miles or 5 kilometers. That's kind of far. Not enough necessarily to change latitude where it's going to be colder or warmer, but then multiply that by like, 10 million years or 100 million years. And you can see how there are some pretty dramatic things happening on Earth as these plates move around. Things that we will be talking about more when I cover Earth's deep time, Alabama's geologic history. Okay. All right. Now, a lot of what we need to do to understand why there's so many species in Alabama and in other places of the world is understand rocks, because rocks create different environments on the Earth's surface, from the soils that arise from them to the different structures that they create in terms of topography. So let's take a look at that. Okay, let's cover some basics first. A rock, so let's start with a mineral. I'm going to define that first. Minerals are elements or chemical compounds that occur naturally in a solid, regular crystalline structure. Okay, what does all that mean? All right, I think and hope that you're familiar with this thing called the periodic table of elements. Those are showing the different atoms that scientists have discovered. And those atoms get arranged in certain ways to form different types of metals. I'm sorry, minerals. And one example of that would be iron ore that we find here in Birmingham. Another might be quartz, like the crystals depicted in the top right. Those are all examples of minerals, okay? A rock is a combination of one or more minerals. So I might be holding a chunk of iron ore, okay? And it's just one mineral in there, just the iron ore. But it's also a rock because it's a chunk of material. Maybe I go to a place where there's some limestone mixed in with this iron ore. Okay, so I've got a rock that's composed of two different minerals. And in some places you can find multiple types of minerals. Look at this. I know it's a crummy photograph down at the bottom right, but check it out how there's a quarter there for size. And you see you're looking at rock, and there's this dark material here, this light brown material here, this kind of weird spongy looking material here, some reddish material. So and then you whatever the matrix is, sort of cementing it all together. There's like 4 or 5 different types of minerals in this piece of a rock that we're zoomed in on looking at here. Okay, all this to say that rocks are combinations of one or more minerals, but a mineral is like the smallest way of dividing rocks down based on what is their composition. Okay, all right, so that's rock versus mineral. Now, rocks, there are 3 different major categories of rocks. You maybe learned this a long time ago, like in elementary or middle school or something like that. There's igneous rocks, metamorphic rocks, and sedimentary rocks. Okay, nicknames for them: fire rocks, pressure rocks, water rocks. You'll see why in just a minute. Now we're going to learn the rock cycle, and this is a cartoon that in a very clear, unimaginative way shows you the rock cycle. And you'll see that there's here your igneous rocks, your metamorphic rocks, and your sedimentary rocks here. And then this shows you how they're all connected to one another, cause and effect, that keeps cycling forever and ever. Now this is a very clear diagram, but I'm going to use this diagram instead to sort of illustrate the different types of rocks. And you can go back and forth. They don't contradict one another. This is just this shows some of the processes that are involved with some illustration. All right. Now, let's imagine, for example, that let's start with a volcano, because volcanoes are cool, obviously. There's a weakness in the Earth's crust. It allows magma, which is molten rock, melted rock, to bubble up and rise to the surface. As it rises to the surface, it eventually cools and forms new rock. Okay, so that type of rock that is formed from molten rock or melted rock, that type of rock is known as igneous rock. And you can have extrusive igneous rock that's up at the surface, like you see here on the slopes of the volcano, or you can have intrusive igneous rocks. This would be like a volcano blob that never makes it up to the surface, but it cools in place. There's lots of these in eastern Alabama and in Georgia and other parts of the southeast, for example. Okay, so both of these would be considered igneous rocks. Okay, fire rocks. They cool down from molten rock. Now, as this material is exposed to the surface up here on the slopes of the volcano, it's exposed to rain and wind, and plants start growing on it, and all sorts of stuff happens to it, breaking off smaller and smaller pieces of that rock, forming soils and so forth. All that stuff is called sediment, and sometimes that gets washed across the landscape, sometimes blown across the landscape. That's called transportation, also known as erosion. Okay, and any rocks that are exposed at the surface, even other types of rocks, are subject to all this, and that material eventually washes into a creek or a stream and then winds up washing out into lakes, or more often out into the oceans. Okay, now that material doesn't float. It's little bits of rock. It's not going to stay suspended in the water very long. It's gradually going to sink, and when it does, it forms these layers of marine sediment, like you see here, these gray bands where my cursor is now. Well, as you get layer after layer after layer after layer of this sediment piling up on top of one another under intense amounts of pressure from the ocean weight and more sediment weight on top of it, it causes the particles to cement together, to actually, instead of being a bunch of sand, the sand cements together and forms, in that case, sandstone, or maybe if it's mud, it becomes mudstone and things like that. Okay, so these types of rocks that are formed from this process of sediment that is getting fused together to make new rock, we call that sedimentary rock. All right, so we've got igneous rocks and we've got sedimentary rocks. Now, the final type of rock that we're going to talk about and learn about is metamorphic rock. Metamorphic rock is when you have either igneous rock or sedimentary rock that is exposed to intense amounts of heating and pressure, or as it says here, deep burial, heating, squashing. I don't know that that's really a geologic term, but it's on here anyway. When you get it all sort of squeezed together under an intense amount of heat and pressure, it changes the physical properties of that rock, usually making it more firm and more dense and heavy. And that new type of rock is called metamorphic rock. Metamorphosis, I think means change, and so you basically changed the igneous rock or the sedimentary rock into this new type of rock. An example of this would be marble. I think you're probably familiar with marble. If not, do a quick Google search and you'll be like, oh yeah, I've seen this stuff. Guess what? Marble is actually the metamorphic rock version of limestone. So when limestone goes through this process, it forms marble. Okay, if we had real classes, I would pass around some rocks for you guys to see, but that would be all sorts of opportunities for COVID and stuff like that to move around. So we'll just not be doing that this class. All right, let's look into weathering, erosion, and deposition just a little bit more here. Weathering, as I told you, is like how rocks are basically broken up by exposure to the elements, as we might say. So that's wind and rain and things like that. And even the growth of plants can cause the weathering of rock. And weathering can be physical, like when you, for example, have small rocks that are being washed downhill, grinding against larger rocks, and the collisions break off particles of the larger rocks as well as the smaller rocks. And that would be an example of physical weathering. But you can also have chemical weathering, and that's what you see here in these pictures here, where out on this section of granite, which is a type of igneous rock, and you can find this over Stone Mountain, Georgia, for example, is formed of granite and some old volcano core. And on the surface of Stone Mountain and similar rock formations in Georgia and Alabama, you get water accumulating on the surface. The natural acidity in water eats away at that rock very gradually, and that's what causes these circular patches like you see here on the front portion of the picture that I have pasted here. That would be an example of chemical weathering. Plants can start growing in there, some very simple plants. This is primary succession. Yep, making the connection here to some earlier ecology. This would be primary succession. The plants gradually build up a little thin layer of soil, and the acidity from the plants as they die and decay eats away at the rock even more. So that's even more chemical weathering. Okay. By the way, just as an aside, there's some really interesting rare plants that can't be found anywhere else in the southeast, but on these type of rock outcrops, which help illustrate why geology is important to understanding the diversity of plants that we have in the state. Okay, so this is weathering. Erosion is the movement of weathered material. So here you see somebody testing soil out in an agricultural area. Clearly there's some erosion here. Some rainfall is washing this farmer's precious soil off of his or her land. That's the process of erosion. It's usually done by water, but it can include wind. You might recall in the summer of 2020, we had some big dust storms from Africa hit the southeast, and you look out across Birmingham and everything's a shade of yellow. Well, that's dust from the Sahara, and that would be obviously wind erosion. Okay, and of course this is the erosion that brings the material out to the oceans or maybe a large lake, and that process is called deposition, where the eroded material comes to rest. And in the right conditions, that can form sedimentary rock, which I've actually already described for you. You get these layers of marine sediments accumulating one on top of the next, the younger ones up at the surface, the older ones buried more deeply. The ones that are buried more deeply are under intense amount of pressure. And what's kind of cool is that under this amount of pressure, it changes the physics of the water. There is water in this sediment. It's like filling up the little spaces between the particles. And under that intense amount of pressure, it makes dissolved minerals come out of the water and form solids. So the classic one is silica. So you can have dissolved silica in seawater, but under that intense amount of pressure, it causes that silica to come out of liquid form and make basically rock, like it forms a solid that sort of glues the sand grains together. And so you wind up going from a layer of sand that might be deposited here, it becomes sandstone, or reef material, like a coral reef material becomes limestone, or mud becomes mudstone, or silt becomes siltstone, etc., etc. And sometimes you can actually, these rocks actually capture ripple marks where ocean currents have sort of left like little wave-like patterns in the rocks. You can see that in some of the buildings and rock walkways around Birmingham and stuff. It's a popular feature for people to use in stonework. Okay, so that's how sedimentary rock forms. All right, so how do geologists know all this stuff? Well, there's old school techniques, like you have these old school geologists out in their khakis and their hats, walking around with pickaxes and shovels and studying the layers and trying to figure things out. And that was really all we had for a long time, and geologists were able to piece together a remarkable explanation of Earth's history with these simple tools and processes. But these days we use newer techniques that involve geographic information systems, things like LIDAR that help us like look at the shape of the seafloor, even using detonations of explosives and then measuring the vibrations as they travel across the Earth's surface through the Earth's crust to make images of like what's going on down there. We're going to study some of the very fundamentals of the techniques, and because it helps us understand geology and appreciate how that geology has shaped all the biology that we're supposed to be learning about, right? Okay. So the first things that we're going to cover are the methods that geologists have used. And again, these are kind of old school traditional methods, but the methods that geologists have used for dating rocks, like figuring out like how old rocks are. And the first method is called relative dating. That means you don't know the exact age of an event that happened or a rock layer that you're looking at, but you know that this rock layer formed after that rock layer. All right. So what we're looking at, this picture will help explain this. What we're looking at here is a one section of the Grand Canyon, and you see the river, the Colorado River, looping around here from left to right. I don't know what's directions upstream or downstream. It doesn't matter. But you can see that the river has carved through lots of rock layers over tens of millions of years, and that's what all these little bands, these little layers are that you see here going up the side of the canyon. And these are all sedimentary rocks that formed on the ocean floor a long time ago, when this portion of the earth was ocean floor. And I'm going to go back a couple slides. So here we go. See these bands here? This is what we're talking about here. And as would have made sense when you looked at this, the layers on the bottom were deposited long ago, and the ones that are up at the top were deposited more recently. We don't know the exact ages when we're looking at this, but we know that these are the younger rock layers and these are the older rock layers. So moving over here to the Grand Canyon, looking at this slope over here on the right, these are the older rock layers here, and these would be the newest rock layers up there. All right, so that's actually tells you a lot of information. It doesn't tell you anything about like how old those rocks are, but it does still tell you a lot about the sequence of events. Okay, so that's relative dating. And by the way, you're going to be using this in a class exercise to kind of piece together some geologic events. All right, we're going to learn two laws, geologic laws, and the first of which is the law of superposition. And that is that basically what I've already told you, which is that older rocks, of sedimentary rocks, older rocks are at the bottom and newer rocks at the top. That's what geologists mean by the law of superposition. And here you see a cartoon illustrating sections of the Grand Canyon, and it's got all the different names of those rocks, and we know that these are the Kaibab limestone at the top is the younger rock, and then this stuff down at the bottom dates all the way back to the Precambrian. Okay, you do not need to learn all these different names of rocks and stuff like that. This is just illustrating this principle. Okay, law of superposition. Now here's your other geologic law, the law of original horizontality. Now I'm going to roll back a slide here. When we go several slides, sedimentary layers, when they form out in the ocean like this, they tend to lay flat like this, like sort of parallel to Earth's surface. Okay, and that's how sedimentary rocks form, is in that situation like that, where they're parallel to Earth's surface. So anytime where you see sedimentary rock layers that are not horizontal to the Earth's surface, where they're kind of bent, like you see over here with these tilted rocks, that tells you that some sort of geologic process happened after the rocks were formed and caused a distortion to the Earth's crust. Okay, so it's kind of like looking at a car that's been in an accident, and you see it's all banged up and the metal is twisted and bent and stuff like that. You know that first the car was made in a factory and it was all looked good and was functioning well, and then there was a collision. And what you're looking at here, this would be analogous to that collision. Okay, it's all been deformed because of some process. What kind of processes lead to this? Well, you can think back to all those processes we learned a few minutes ago. Subduction zone, divergent plate boundaries, and of course the one I'm blanking on, let's see, subduction zone, spreading, so divergent plate boundaries, and transform faults, of course. Yeah, those three different forms of fault lines along the tectonic plates. You can also get distortions of rock away from the edges of tectonic plates. We see plenty of that as well. Okay, so these two laws, horizontality and superposition, geologists use that. They could piece together the sequence of events that have occurred when looking at a series of rocks. And you're going to practice that in class, in our class session. All right. So what we've been talking about so far, rolling back to here, this is relative dating, figuring out the order of events to explain things at the Earth's surface. Now, the second thing we want to look at is another dating method called correlation of rock layers. So we use those two laws that we just learned about and compare rocks from different regions, matching rocks of shared types to figure out what has happened. Now, here's an example. In this cartoon at the right, we've got some sections of the Earth's crust that are exposed, and geologists have mapped them out and drawn different patterns here to represent different rock layers. These little symbols in here represent different types of fossils found in those rock layers. You know, sedimentary rocks, I didn't mention this before, but sedimentary rocks usually have some fossils in there. Usually they are marine creatures that lived on the seafloor or above the seafloor, and then when they died, they get stuck in those sediments and they become part of the rock. That's how a fossil forms. And so these rock layers on the left are being compared by geologists with these rock layers that are on the right. And these areas might be tens of miles away, sometimes hundreds or thousands of miles away. And geologists can piece it together, the age of the rocks based on the fossils, because organisms that can be spread out over, so animals can be spread out over huge areas. And I said animals, but it's plants too. But they might be living and becoming fossils in different types of rocks. So for example, check out this little spirally looking snail thing here. On the left, that species is a fossil in some limestone. And on the right, that same species that's identical when you compare them is a fossil in some sandstone. So on the other side of this ocean basin, maybe other opposite sides in the Mediterranean, I don't know, whatever. When geologists find the same fossil species but in different rock types, that tells them something. It tells them that those two rock types, the sandstone on the right and the limestone on the left, they formed at about the same time. So that provides geologists even more information about how the sequence of events that led to what we see in the rock today. All right, moving on here. So that's dating method 3. Correlation of rock layers. Yeah, okay. I kind of messed that up. Now I'm not going to re-edit this. Let me back it up here. I've given you two methods in a lot of detail. Number one is relative dating. Number 3 is dating with fossils. Okay. Number 2, we're going to go over a class exercise. We're going to do a class exercise that's going to drive this home. Is correlating rock layers over long distances. Okay. Sorry about the confusion there, but you got three different dating methods, and one of which we'll go over in our synchronous class session. All right. So everything we've looked at so far is about the relative ages of rocks, but geologists actually can pinpoint the timing of some events. Otherwise, when we had that geologic time chart at the very beginning of this presentation, we wouldn't have dates on there. So how is it that geologists are able to pinpoint the timing of these events? And they use a method, there's several methods, but these are, instead of relative dating, we call all these methods absolute dating, because you're actually not looking at the general sequence of things, you're actually being able to say, hey, this event happened 324 million years ago. And here's how we understand that. Okay, that's what they mean by absolute dating. All right. Now, these dating methods involve using radioactivity. Now, we don't need to get into a lot of detail here, just what's on the slides. But here's what you need to know: is that atoms, which are the most fundamental unit of matter, atoms which are composed of neutrons and protons, and then these little electrons that spin around them, and so forth. Atoms can, for some different types of elements like carbon, they can come in stable and also unstable forms. So at the very bottom, for example, you see the three forms of carbon. There's C12, C13, and C14. The C stands for carbon. The 12 stands for the number of protons and neutrons that you find in the nucleus of the atom. All right. What's interesting and helpful in geology is that the unstable forms of the atom, they don't like to stay unstable. And what will happen is that over time, they will throw off a particle and go from having 14 particles in the nucleus of the atom to down to 13. And sometimes the 13s will go down to 12. Okay? So carbon-14, you might have heard of carbon-14 dating as a way of dating, like, materials that geologists find or paleontologists find. You can measure how much radioactive carbon is in a material to figure out how old it is when it comes to rocks. All right. Now, we got some terms here. The unstable versions of these atoms, we call them radioisotopes. Isotope is simply a term for multiple versions of these atoms, kind of like alleles, it occurs to me to mention. Remember, we learned about alleles are alternative versions of the same gene? Well, isotopes are different versions of the same atom. All right. Now, the reason why geologists are able to use this radiation to date rocks is because, and this is pretty cool, I think it's cool, is that the rocks, when they are formed, they start off with a certain amount of radiation of, say, carbon or other types of atoms, and then the unstable atoms, they switch to a stable state at a relative rate. So you can think about it like they're leaking, and they're leaking out these particles and going from an unstable to a stable state. And you can tell how old a rock is by measuring its level of radiation. If it's got a lot of radiation, it's a relatively young rock. If it doesn't have as much radiation, it's a relatively sorry, I had to pause there to make sure I said that right. Yeah, if the rock has a lot of radiation, it's relatively young. If it has less radiation, it's much older. So, for example, volcanic rock, when it's spewed out on the surface and it cools, it around the world, it all starts with about the same amount of radiation. And you can go to geologists can find any igneous rock anywhere, measure its radiation, and tell you within like a couple of million years how old that rock is. And so this is the kind of work that geologists do to date rocks. What I really want you to get at here is that they use these radioisotopes to date rocks. It's involving radiation and radioactive decay, and that it gives us some precise dating tools, some absolute dating tools. That's what this is all about. I'm not trying to drive us crazy here with lots of like detailed stuff about atoms, but I also want you to understand that the science that's behind this stuff, rather than just sort of accept it that yep, this rock is 300 million years old. I want you to know a little bit about why. Okay, I'll let you study this on your own. It's an example of how to use carbon-14 to date out some rocks, and this should be self-explanatory. If not, ask me a question about that. And I mentioned this already, that volcanic rock has a signature level of radiation, which allows volcanic rock to be really useful when it comes to dating events. Okay, so in the next class video lectures, we're going to go through deep time, Earth's deep time, and you're going to see lots of maps like this. The Earth, of course, wasn't shaped like this way back then, but this is a way of mapping the Earth's surface so you can see everything. And what you're looking at, continents and oceans, and then the white represents the boundaries of the modern day continents. And the important thing is that I'm trying to get at here is that there's a date. This would be 237 million years ago in the early Triassic period. Okay? The reason that we can say this is what Earth looked like 237 million years ago, is through a lot of work by generation after generation after generation of geologists using both relative dating techniques and then later on using adding some of the absolute dating techniques to figure out the sequences that have occurred to shape the geology that we have on the modern Earth's surface. Okay. All right, so that's a wrap, folks. It's your basic introduction to geology by your biology professor, and we will. I'll take questions from you guys in class, of course, and we'll do some class exercises to practice doing some relative dating and things like that. Okay, that's a wrap, folks. Talk to you soon.